All right, so let's go ahead and get started here. So this is trigonometric equations, and I'd like to kind of make a distinction here to start between trigonometric identities and trigonometric equations. So a trigonometric identity is what we did in our last section, 7.1. And I said that those are equations. So I can understand why you get these two confused, but it is kind of important to understand the difference. So an identity is an equation, but it's an equation that is always true, no matter what the variable x is, such as sine squared x plus cosine squared x equals 1 is my favorite trig identity. If you have a different one, you can put it there. If you like 1 minus cosine squared equals sine squared, you can put that. Or cosecant of x equals 1 over sine x. That also works. But I like this one. And so remember and this is kind of going back to these types of problems that we did here. Our goal on this one was not to figure out what the variable was, right? We weren't trying to like find x equals or theta equals some number, okay? We were just trying to make the right side look like the left side or make the left side look like the right side. So what we're doing today is a little bit different. Today we're doing trig equations, and these are equations that involve a trig function. We must find all values of the variable that make the equation true. So there will sometimes just be one kind of number that makes the one angle that makes it true. Sometimes, more often, there will be 2, sometimes 4 correct answers. And we are going to have some that have an infinite number of answers. We're actually going to have a lot that have an infinite number of answers. And we'll kind of explain how we write an infinite number of answers, because there is a specific way. But I will teach you. Yes, that's my job, right? All right. So let's go ahead and get started with the first one here. Okay, so it says for these ones, when you just have one trig function, so we just have the sine x right here. First of all, we isolate the trig function. That's kind of, I think, the easy part. So for this one, we'll add the 1 over. So we get 2 sine x equals 1. Divide by 2. So sine x equals 1/2, okay? So that is us isolating the trig function. Next step is that we look at the unit circle and we find all the spots where that's true, okay? Oh, quick note. So we're actually going to be answering 2 questions here. We're going to be doing part A first. So part A says find all the solutions between 0 and 2 pi. So that's like all the solutions on our first trip around the circle, okay? Then part B says all real solutions. I will tell you that on our web assign for this, most of the questions are asking you for part B. So I'm going to go ahead and highlight that, all real solutions, all right? But the good news is you kind of need part A in order to do part B. They're definitely connected, and we'll see that as we go forward here, okay? So let's go ahead and answer part A here. Where does sine x equal 1/2? So I got to look at my unit circle now. Let me zoom in a bit. I'm going to put this a little, oops, that's not what I meant to do. Let's put this a little closer. Let's do a little zoom in action. Okay, so they give us a good reminder here that these points are cosine comma sine. All right, so the x value is cosine and the y value is sine. So remember that. So when we're looking for sine of x to equal 1/2, we're looking around the unit circle for a y value of 1/2, okay? So where do we find a y value of 1/2? Well, I definitely see 1 right here at pi over 6. Notice that the y value at pi over 6 is 1/2, right? So I'm going to go ahead and say here x equals pi over 6. So it's kind of backwards from how we used the unit circle before. So before I would say like, what's sine of pi over 6? So you would find you would find pi over 6 on the inside and then look at the y value on the outside and say, okay, that's 1/2. Now I'm saying, like, where does sine of x equal 1/2? So we're saying, okay, I got to look on the outside, find a y value of 1/2. And my answer is the angle on the inside. You know what I'm saying? All right, cool. But there is another spot on the unit circle where sine of x also equals 1/2, okay? So let's take a look around the unit circle, see if you can find another spot on the unit circle where the sine is equal to 1/2, or said another way, where the y value equals 1/2. So I see it right here at 5 pi over 6. You see, we also have a y value of 1/2 right there. All right. Are there any other spots on the unit circle where the sine of x equals 1/2? I'm going to say no, okay? What about 7 pi over 6 down there? Does the sine equal 1/2 down there? No, the sine equals negative 1/2. So that's not what we want. We want a positive 1/2 instead, okay? There might be another problem where we want a negative 1/2, but on this one, we want a positive 1/2, okay? All right. What about 5 pi over 3? Is the sine 1/2 there? No, the cosine is 1/2 right there, right? So we need to find the sine equals 1/2. So I'm going to box that up. This is going to be our answer for part A. Between 0 and 2 pi, there's only two spots, pi over 6 and 5 pi over 6. I will tell you that usually when your trig function equals a single number, you're going to get two answers for part A. Almost always. There are a couple exceptions for that, but almost always you'll get two answers, okay? When your trig function equals a single number. All right, so now let's move on to part B, which is kind of the more important part for WebAssign, which is all real solutions, okay? So what are all real solutions? Let me kind of explain this. So we know that pi over 6 is a solution, correct? But remember coterminal angles, all right? Coterminal angles, we talked about those. And that said that if you add 2 pi, you get an angle that's in the same spot. And if it's in the same spot, it has the same sine, cosine, tangent, and everything. So if I take pi over 6 and I add 2 pi, I go all the way around the circle. I'm back to the same spot. Technically, the spot is now called 13 pi over 6, which is greater than 2 pi, but it does still have a sine value of 1/2. Then if I add another 2 pi, I'm technically at 25 pi over 6, but it's really in the same spot. And so it still has a sine value of 1/2. And so I could just keep adding 2 pi forever and keep getting those correct answers. So should I start writing that out? Pi over 6, 13 pi over 6, 25 pi over 6, 37 pi over 6, and keep going forever? No, that doesn't make sense, right? We can't do that. We don't have time. So here's what we do. It says over here, for part B, add 2 pi k for sine and cosine. So let's go ahead and do that now. So what I'm going to do is I'm going to write x equals, I'm going to write my first answer plus 2 pi k. And then I'm also going to write my second answer plus 2 pi k. So that'll be our answer for part B. But before we move on, let me ask the question that my 3-year-old son asks me about every 10 minutes. Why? You know what I'm saying? Yeah. All right. It's kind of annoying. But not from you guys. You guys can ask me why, okay? So here's why. Let me explain. K here, K represents any integer, okay? So what I'm saying is I can plug in any integer for K on either one of these formulas, and I will get another correct answer, all right? So let me explain. Technically, 0 is an integer. So if I plugged in 0 for K, and let's just focus on this first formula for now. You could do all the same things for the second formula, but if I plug in 0 here, all of this goes away, and I'm saying pi over 6 is a correct answer, which we know from part A it is. If K is 1, it's saying take pi over 6 and take a complete trip around the circle, 2 pi. That would be 13 pi over 6, and that's another correct answer. If K is 2, that means take 2 trips around the circle, end up in the same spot. That would be 25 pi over 6, and that's another correct answer. So every time I plug in another integer for K, I get another correct answer. I don't actually have to do that, but it's saying that if I wanted to, I could, okay? So this is how I get my list. It's like a formula for all the infinite number of correct answers that there are to this question, okay? So that's our answers for A and B for number 1. All right, cool. All right, so we're gonna move on to number 2 now and try this again. So I'm gonna move my unit circle over here. Okay, number 2. So once again, we need to isolate the trig function first. So let me do that. I'll go ahead and switch colors here. So I'm going to subtract the 3. Oh no, why are they doing this? Ah, I know it's reading my pen because I can see the little dot, but it's not writing. Maybe purple will work. No, it will not. Okay, there we go. All right, so we'll subtract the 3 over here. We get cotangent of x equals 0, okay? Okay, now, whenever I have one of the weird reciprocal functions, I usually like to switch that, all right? So I do the reciprocal. So this one's a little bit weird, but let me kind of do a little thought bubble up here. So I'm gonna say if secant x equals 2, then I would switch that to say cosine x equals, and it would not be 2, it would be 1 over 2, right? It would be the reciprocal. So whenever I get secant or cosecant or cotangent like that, I always switch it to the one of the normal 3 trig functions, sine, cosine, or tangent, all right? I just think that makes it a little bit easier. You could still do this using secant or using cotangent. I just think it's easier to switch it to one of the normal ones. But just remember, as you do that, you got to do the reciprocal of the number, right? So this one's a little weird because if cotan of x equals 0, and I can think of that as kind of like 0 over 1, what that really means is that tan of x is actually undefined. Remember that 0 over 1 is 0, but if I flip that upside down, right, that means that I have 1 over 0, which is undefined. Let's also remember that tangent is y over x. And so when I go to the unit circle right now, what I'm looking for is I'm looking for a 0 in the denominator. And so I'm looking for a 0 for my x value. If I can find a 0 for my x value, that would be an undefined tangent. It would also mean that cotangent is 0. So I think we're ready to answer part A now. Let's see if we can find, and I'll tell you again on this one, there's going to be 2 spots on the unit circle between 0 and 2 pi. Where the tangent equals the tangent is undefined, okay? Where the x value is 0. So I'm going to say the first one is up here, pi over 2. You can see that the x value, if I did the tangent there, y over x, it would be 1 over 0, which would be undefined. So pi over 2 is going to be my first answer. All right, now there is another spot where we have an x value of 0, which would give me an undefined tangent. If you haven't seen it yet, here it is, 3 pi over 2. The tangent there would be negative 1 over 0, but negative 1 over 0 is still undefined. So 3 pi over 2 will be my answer there. Those are the only 2 spots where I have an x value of 0, giving me an undefined tangent. All right, so now let's move on to part B. Now part B is going to be a little different, so hold up. Don't answer part B yet. Let me explain something. If we go back over here, I said over here that we're going to add, for part B, we're going to add 2 pi k for sine and cosine, but we're going to add pi k for tan or other diameter buddies. All right, so what's a diameter buddy? Well, that's actually not a technical math term. That's a Mr. Barryism right there. I kind of just made that term up. A diameter buddy is an angle that's on the opposite side of the unit circle from you, okay? So it's on the exact opposite side. If I was to draw a line between the two angles, I would have to go through the center of the circle. So you can see that pi over 2 and 3 pi over 2 are diameter buddies, right? You have to go through the center of the circle to connect them. Going back to number 1, when we had pi over 6 and 5 pi over 6, you can see that these are not diameter buddies. If I connect those two angles, it does not go through the middle of the circle. If I was going to do pi over 6's diameter buddy, I would say it's 7 pi over 6, okay? All right, so these two are diameter buddies. And so what that means is, when I'm writing my formula for part B, I can actually connect them. I can actually write both of them with just one formula, okay? And so for the formula, I take the first one only, and then I add pi k. So I don't add 2 pi k like I did in number 1, since these are diameter buddies. I can get them both by just doing the first one plus pi k. Now, why am I allowed to do that, okay? Well, I can explain it 2 different ways, and I will. So the first way is, if you actually look at this, and let's say I plugged in 1 for k, and I did pi over 2 plus pi times 1. Well, if I did common denominator here, that would be pi over 2 plus 2 pi over 2. And you can see that would give me 3 pi over 2, which was my other answer. So you can see this one formula covers for both of the answers in part A, okay? Because the distance between them is pi. The other way you can think of that is, this is visually, if you look at the unit circle, remember that pi radians is halfway around the circle. And so if I'm starting at pi over 2, I'm saying I add pi and I go down here and there's another answer. Then I can actually keep going. I can add another pi and I'm back up here and that gives me another answer. And I can add another pi and I'm back down there and it gives me another answer. So that's the reason why we do that for diameter buddies. If you didn't care about that and you just want to remember that if they're diameter buddies, if they're across from each other on the unit circle, you just do the first one plus pi k. I'm actually okay with that as well. All right. Awesome. All right, so let's move on to number 3 now. I'm going to bring my unit circle along with me. All right, so let's see the instructions here. If you have 1 squared trig function, you're going to isolate the trig function, and then we're going to square root both sides. Anytime we square root both sides of an equation, we need a plus or minus on the number side, okay? All right, so let's go for it here. So for number 3, I'm going to go ahead and add the 3 over. So I'm going to get tan squared of x equals 3. I didn't actually show my work of myself adding the 3 over, but I hope you guys get the idea of what I did there. I added the 3 over. I didn't show my work on that because I'm a rebel. Yeah, look at me doing math without showing my work. Going crazy today. I don't know. To me, it's like, after we did like the crazy stuff from last section, all those like trig identities that are all super difficult, it's like, all right, now you want me to show my work adding 3 to the other side? Like, we get it. Add 3. Okay. All right. Next up, necesitamos tomar el raíz cuadrado a los dos lados, claro. Okay. In English, I need to take the square root of both sides, of course. And so I'm going to say then tan x equals, and this is where I need to make sure I remember to put the plus or minus in front. And then I don't really know what rad 3 is, so I'm just going to call it plus or minus rad 3, right? We know it's some decimal, but we're going to leave it as rad 3. Plus or minus rad 3, excuse me. Okay, so now we need to go to the unit circle and find all the spots where tangent of x equals either rad 3 or negative rad 3, okay? Now, I told you guys that when your trig function equals one number, like on number 1, when it equaled 1/2, we got 2 answers for part A, correct? Now, I'm going to argue that our trig function actually equals 2 numbers. It equals rad 3 and it equals negative rad 3, correct? So now what that's going to do to our answer to part A, instead of getting 2 answers, we're going to get 4 answers. It's going to double our number of answers because we're now equal to positive rad 3 and negative rad 3. Whenever it's a plus or minus like this, you're going to get an answer in all 4 quadrants, okay? And it's going to be related. So once you find kind of the answer in one quadrant, it's going to tell you the answer in all 4, and I'll show you how, okay? So let's start off with quadrant 1. So in quadrant 1, if we're looking for tan x to equal rad 3, tan is a little trickier here because you can't just like look at it, like cosine and sine is just on the unit circle. But for tan equaling rad 3 in quadrant 1, I would say it's got to either be pi over 6 or pi over 3. I know that because those are the ones that have the rad 3 in there. You see that? So pi over 6 has the rad 3 as the x value. Pi over 3 has the rad 3 as a y value. So which one of those is going to give me a tan value of rad 3? I actually know that it's pi over 3. How do I know that? Because, I don't know, I've been doing this a long time, but we can always test it. So let me test it here. So what is tan of pi over 3? Well, we know that tan is y over x. So I would do rad 3 over 2 over 1/2. If we multiply by the reciprocal, we'll get 2 over 1. And so that would, tan of pi over 3, you can see would equal rad 3, okay? So that is what we were looking for. We were looking for the tangent to equal positive rad 3 or negative rad 3. And so we have found that at pi over 3. I wasn't sure if that was the spot. So that's why I did this little test over here. If I do y over x, will it come out to rad 3? We see it did, right? So then I told you that once we found it in the first quadrant, it was going to be really easy to find it in the other 3 quadrants. Because we have plus or minus, it'll be in all 3. So the next one I'm going to say also will work as 2 pi over 3. Because if you look at the coordinates here, negative 1/2 comma rad 3 over 2. If I did the y over x there, it would be kind of the same as what I did here, except it would come out to negative rad 3. Now, negative rad 3 is okay for me on this problem because I have that plus or minus, correct? Plus or minus means it's okay if it's positive rad 3 or it's okay if it's negative rad 3. So 2 pi over 3 would be negative rad 3, but that's still okay. If I go down to the third quadrant, 4 pi over 3, you can see is negative 1/2 negative rad 3 over 2. It would create that same fraction that I did for pi over 3, except they'd both be negative. So that one would actually come out to a positive rad 3, which is acceptable to me in the plus or minus. And then I hope that you can guess what's going to be our answer in the fourth quadrant now. We had pi over 3 in the first quadrant, 2 pi over 3 in the second quadrant, 4 pi over 3 in the third quadrant. And if you guessed 5 pi over 3 for the fourth quadrant, you are correct. So we noticed that all of the denominators are the same here, correct? All right. So those are our 4 answers. 1 from each quadrant, like I said before, twice as many answers as we got for numbers 1 and 2 because our tan function was equal to a plus or minus instead of just one of them. All right, so let's move on to part B. Now, part B, out of my answers for part A, do I have any diameter buddies? I'm going to say yes. I actually have two sets of diameter buddies. We see pi over 3 is diameter buddies with 4 pi over 3. They're across from the unit circle from each other. So when I'm writing my formula for part B, I would just write the first one plus pi k. Then I have another set of diameter buddies here. 2 pi over 3 and 5 pi over 3. So once again, I just write the first one plus pi k. So my first formula covers pi over 3 and its diameter buddy 4 pi over 3. My second one covers 2 pi over 3 and its diameter buddy 5 pi over 3. Boom. All right. All right, let's move on to number 4. All right, number 4. Once again, we're going to isolate the squared, take a square root. So I'll say 2 cosine squared x equals 1. Cosine squared x equals 1/2. Let's take a square root of each side. So cosine x equals plus or minus, since we took a square root. The square root of 1 is just 1, so I'm going to leave that as 1. And the square root of 2, I'll leave it as rad 2. All right, so this is where we look into the unit circle and try to see if we can find a cosine value, which we know on the points is the x value of 1 over rad 2. Now, I'll warn you that it's not there, okay? Except it kind of is there. It's there in a different form, all right? So as we look at the unit circle, we see all the radicals are in the numerators. So I know I haven't really stressed the rationalizing the denominator in this class, but in this case, you kind of have to. So I'm going to multiply the top and the bottom by rad 2. So what I'm really looking for here is cosine of x equals plus or minus rad 2 over 2. So rad 2 over 2, we are going to be able to find on the unit circle. Since this is plus or minus, once again, we're going to find 4 answers. We're going to find 1 answer in each quadrant. So the first answer will be pi over 4. We see the cosine value there is rad 2 over 2. The next answer I would say is 3 pi over 4. The cosine value there is negative rad 2 over 2, but once again, since we have that plus or minus, the negative is okay with us. Next spot I would say is 5 pi over 4, cosine value of negative rad 2 over 2. Once again, the negative is okay with us. And then the last answer would be 7 pi over 4. With the cosine value of rad 2 over 2. All right. All right, next question. Writing my answer for part B. Do any of those answers for part A, are any of them diameter buddies? The answer is yes. Pi over 4 is diameter buddies with 5 pi over 4. You can see that they're across the way here on the unit circle. And 3 pi over 4 is diameter buddies with 7 pi over 4. You can see they're across the way here on the unit circle. But wait a minute, Mr. Barry. So this means that if they're diameter buddies, we're just going to do the first one plus pi k. And that's going to cover pi over 4 and 5 pi over 4. And then for the other set, we're going to do the first one plus pi k as well. Yes, we are. So the second formula covers 3 pi over 4 and its diameter buddy 7 pi over 4, okay? Now, wait a minute, Mr. Barry, hold up. All right. Didn't you say back here that adding pi k was just for tan? And I'm going to say, no, I didn't, okay? I said adding pi k was for tan or other diameter buddies, okay? So I'm going to say here, sometimes sine and cosine, all right? Diameter buddies will come up every time for tan, but sometimes for sine and cosine, so you have to look, okay? So why did it happen there on number 4? Well, it really happened because of the plus or minus. So very often when you have the plus or minus, it's going to create diameter buddies even for sine and cosine, all right? So once again, diameter buddies across the way on the unit circle, they will be part of your answer for part A every time for tangent and sometimes for sine and cosine. So you just have to check. All right. Awesome. All right, let's actually jump ahead to number 6 here. Go ahead and bring my unit circle with me. We'll see how far we get here. We might not be able to finish number 6, but we'll go ahead and start it. Okay, so number 5 and 6, we have multiple powers of the same trig function. So anytime that happens, what we're going to want to do first is get one side to 0. Move everything to one side by adding or subtracting. So in this case, I'm going to subtract tan x from both sides. Now these are unlike terms, so I'm just going to write them separately like this. All right, and then the next thing I have to do in these problems is factor, okay? So I'm actually, in this case, the only way I can factor is GCF. So what's the common factor between these two terms? It would be tan x. All right, next step, I would split these up, set them equal to 0. So this one would say tan x equals 0. This one would say 3 tan squared x minus 1 equals 0. Now I need to isolate tan x on both of these. Now the first one, it's already done for me. Tan x equals 0, done. This one, I'm going to add the 1. Actually, I don't even want to show that. Never mind. I'm just going to say 3 tan squared x equals 1. I'm going to say tan squared x equals 1 over 3. Divide the 3 over. Now I'm going to take a square root. I need to put a plus or minus in front of the number because I created that square root. Then the square root of 1 is 1. The square root of 3 is rad 3. And I know I told you you kind of need to rationalize the denominator. That's really only for sine and cosine. For tangent, you can just leave it like this. That's fine. We'll be able to find that on the unit circle, okay? All right, so now we're ready to answer part A here. And I'm going to need my unit circle for that. So I'm going to start off, where does tan of x equal 0? Well, remember, tangent is y over x on the unit circle, right? So I would want that 0 in the numerator. So I would want the 0 to be y. So I would say that that is there at 0. We have the 0 in the y position. And also at pi, we have a 0 in the y position. So we get 2 answers from that one, tan x equals 0. And then this one, since it's plus or minus, should give me 4 more answers. So I'm going to get a total of 6, okay? All right, so where does tan x equal 1 over rad 3? I'm going to say it's right here at pi over 6. We can see that tan of pi over 6, if we tested it out, would be 1/2 over rad 3 over 2. And if you multiply by the reciprocal there, 2 over rad 3, you would get 1 over rad 3, correct? So that means that pi over 6 is correct. And then since I have plus or minus here, I can do a little shortcut, because plus or minus, I know it's going to appear in all 4 quadrants. And it's going to be all the ones with the same denominator, like we saw before. So all the over 6's then, because it's plus or minus, are all going to be answers. So 5 pi over 6 would be a negative 1 over rad 3. 7 pi over 6 would be a positive 1 over rad 3. And then 11 pi over 6 would be a negative 1 over rad 3. So those are our 6 answers. Whew. All right, we are going to do part B tomorrow because we're almost out of time here. So come back for part B tomorrow of this question plus some more questions. Homework tonight, I have not yet posted the web assign for this. So I would say if you want to get something done tonight, if you have less than 90% in any web assigns from this semester, especially from this unit, but really from all of them, work on those, okay? If you get those up to 90% and send me a picture, I promise it will help your grade more than you think, okay? So that's all I got for today. I'll stick around a minute for questions, but if you don't have any, we will see you tomorrow.